Okay, so we can start. Happy March. So we have Nick Choksi today from UC Berkeley. Now a big fan of planets. So today he's going to talk about planet formation, close to the star, far from the star. Please start.
Thanks. I'm going to divide this talk into two halves. In the second half, I'll talk mostly about close-in planets found by Kepler and TESS, mostly rocky sub-Neptunes. In the first half, though, I'll talk about gas giants orbiting at tens of AU. We're motivated in particular by these images from ALMA that show these dark annuli in circumstellar disks, these gaps. By analogy to shepherd moons, which carve gaps in planetary rings, we think that there are gaps orbiting in the planets orbiting in the circumstellar gaps. Having yet imaged the planets in the gaps, that's where I'm going in the last few slides of this first half of the talk. But for now, there's a suspicion of planets in the gaps. So these are protoplanets. They're still in circumstellar disks. We would like to know how fast they're accreting. Fundamentally, this is the plot that we want to pin down that underlies like half of planet formation. You take a planet of some mass m, you put it in a disk of gas, and you want to know how fast it accretes gas onto itself. So here's a compilation of some studies. These are planet disk simulations that have tried to fill in this exact same plot, m dot versus m. And you can see there isn't really any consensus in anything, let alone even in the scaling. So this is the question I'm going to try and revisit today. For a planet in orbit around a star, the first length scale that comes to mind is the Hill sphere, which grows as m to the 1/3. So the usual thing to do in your planet disk simulation is to make sure, what all of these studies do, is they make sure that you're resolving the Hill sphere with some tens of grid cells. But for a planet in orbit around a star, in orbit in a disk, there are at least two other length scales in the problem. There's the planet's Bondi radius, sphere of influence to gas pressure, and there's the vertical height of the disk that you're embedded in. So what I'm going to show you today are a set of simulations that we've studied. These are 3D planet disk simulations where we're always making sure to resolve the smallest of these three scales. So I'm going to start over here at the left end of the plot, the smallest planet masses, where the Bondi radius is the smallest scale in the problem. And then I'm going to work my way towards higher and higher masses, and we'll see in the simulations how results change. And they'll coincide with reorderings in these length scales. So these are global planet disk simulations. Here's a top-down view of the disk. Here's a gap, an annular gap carved by the planet, high-density spiral waves launched by the planet. You can zoom in into the circumplanetary region. There's all these complicated flows, horseshoes, shearing trajectories. I've color-coded the material that crosses the Bondi sphere in black, has some chance of getting accreted. Can zoom in some more. So this is x, y, and now we're doing z over here. So this is a vertical slice through the disk. The planet is at the origin here. You can see material flowing onto it into the Bondi sphere, more or less spherically symmetrically here. Here, what I'm doing is I'm assuming the planet it's modeled as a sinc cell. Okay, so it accretes everything that gets really close to it. Here I'm showing the same simulation, same planet mass, same everything. All I've done is change the inner boundary condition at the planet. I've removed the sinc. Now the planet is just like GM over R. It's a softened gravitational potential. And when you do that, the whole flow structure changes. Material comes in mostly from above, and then it leaves through the midplane. There's no net accretion in this simulation. We measure how much is coming in blue and how much is coming out in red, and they're in balance. And we think that makes sense. There's like no rocky core in the simulation for material to like slam onto and shock and dissipate all its energy. These are emissive simulations, so there's no way to get rid of your angular momentum. So the gas has nowhere else to go but back out. So people report these flow structures all the time, call them meridional flows. Some people call them decretion disks or recycling flows around planets. But I think it's a numerical artifact of your boundary conditioning. That being said, I do think there are things that can be robustly measured from this kind of simulation. I'm going to focus on the blue, the material which is just coming in, the inflow. Turns out that the amount of stuff coming in, m dot in this simulation and in this one is the same. It's within a factor of 2. And in particular, all of the scalings are the same. The mass inflow rate and how it depends on planet mass and disk properties, those are unchanged. And the reason for that is that the flow is supersonic. You're inside of the Bondi sphere, which by definition is the sonic point in the textbook problem. So what's happening down here and up here, for the most part, they can't talk to each other. They're out of sonic contact. So I'm going to focus on measuring this m dot in, which we think is a maximum on the planet's accretion rate. Okay, we're going to bound the problem. It's not an Eddington, like feedback limited kind of maximum. It's a supply limited maximum. You're always fed the same amount. And what you choose to do with it, whether you eat it all up or spit it back out, that's what depends on this uncertain boundary condition.
Next question.
Sure, yeah.
What about zero crossing in the vertical direction?
Sorry, what about zero crossing?
Are the conditions such that you would ever cross the horizontal line?
Oh, these are, you mean what's happening at z less than 0?
Yeah.
Oh, these are midplane symmetric simulations. Yeah, so, yeah.
Can't cross it.
Yeah.
And the equation of state is.
This is isothermal. This is isothermal. The motivation for isothermal, there's 2 motivations. One is runaway, and in classic runaway giant planet formation, cooling is fast. The second motivation is that we're trying to bound the problem. And isothermal is as fast as you can cool, so again, it's a maximum on the accretion rate.
Sorry, so just on this, is having a sink the more or less realistic?
Okay, so there's history. Yeah, well, okay. Realism, the physics depends, I think, on stuff that's happening very close to the planet, circumplanetary physics, how angular momentum is transported in like a circumplanetary disk, which I don't think we understand. I don't know. These are 2 limiting cases, and which one is more appropriate, I think is unclear right now. Yeah.
That would actually depend on the cooling to assume is immediate.
Yeah, it may not be isothermal down here. Okay. I continue to hope that like out here, what's happening out here and down here don't talk to each other because of the supersonic nature of the flow. Okay, so here are our mass inflow rates measured from the simulations. So you just take a shell, you add up how much mass is crossing it per unit time. This plot is showing you it doesn't really matter which shell you take. There's a nice steady flow all the way down to the sink. We've got a whole bunch of planet masses here, different disk temperatures. The temperature of the gas is measured here by the aspect ratio of the disk. And we're looking for some understanding of how the simulation results are scaling. Most naive model for how gas accretion works is Bondi accretion, which describes spherically symmetric accretion onto a point mass and infinite uniformity of gas. And we can check to see whether these 3D global planet disk simulations resemble at all Bondi. So the way I'm going to do this, I'm going to take all these simulation curves and I'm just going to normalize them all by the classic Bondi scalings. M dot goes like m squared and 1 over c cubed. Let's do this. This is a factor of 200 here. normalize everything by Bondi, and it's all like totally self-similar at the 10% level. The reason we are recovering Bondi in this big global simulation is that the planet's Bondi radius is small. It's small in particular compared to the vertical height of the disk. So from the planet's perspective, it does kind of look like it's embedded in this infinite sea of gas. Now you don't continue at Bondi forever. So these are higher masses now. At higher masses, we get not m dot goes like m squared, but m dot goes like m to the 1. Go to even higher masses, super Jupiters now. M dot goes like m to the 2/3. So it's getting weaker and weaker. From squared to 1 to 2/3. You can understand these new power law scalings too. Qualitatively, the reason things are changing is that the scales have swapped. The Hill sphere now sits inside of the Bondi sphere. So your bottleneck for gas accretion, it's not gas thermal pressure anymore. It's like the tug of war with the stars. Stellar tides trying to rip material away from the planet. So that's the qualitative picture. You can do the quantitative too. You can get this power law index. You can write any accretion rate as a mass flux rho v multiplied over an area that you're accreting. So the relevant area now is like r Hill squared. And material is being fed into the Hill sphere on more or less Keplerian orbits. So the velocity with which you're coming in is 3/2 omega r Hill. It's a relative velocity in the frame of the planet. So r Hill goes like m to the 1/3, so you get 1 power of 1/3 from the velocity, 2 more powers of 1/3 from the area, and you add them up and you get m dot goes like m, which is what you measure in the simulation. At higher masses, this slightly weaker scaling, it comes from the fact that these planets are so big now. They're so big that their Hill sphere actually exceeds the vertical height of the disk, the scale height. Okay, so this is a cartoon of a vertical, the cross section of the disk, and the planet can reach all of this stuff at very high altitudes. Its sphere of influence reaches up there, but the density falls off past the first scale height super quickly. So there's like actually very little to accrete up there as sort of a practical matter. So the effective area that you're feeding off of is this sort of folded rectangular cross section. So it becomes more of a 2D problem now. You expand you increase your mass, you're only getting more stuff to eat from the equatorial direction. So qualitatively, that's why you go from 1 to 2/3.
So the size of the Hill sphere depends also on the semi-major axis of the planet, right? Around the star.
Yeah. Everything will scale with A. Yeah. It's suppressed in here, but yes. So here's just a summary of everything I've shown you so far. These are inflow rates in synkless simulations, accretion rates in sync cell simulations, plotted against the mass of the planet. This is a dimensionless, the thermal mass parameter for those who are familiar, dimensionless mass. Points are simulation results, and then overplotted is our analytic understanding. So we have these 3 regimes, and which regime you fall in just depends on how these length scales order relative to each other. And I've emphasized it less, but the same scalings also work to describe the dependence on the temperature of the disk. You can try and test these scalings against protoplanets. We only know of 2 so far, confirmed. This is in the PDS-70 system. So here's the disk around the star, imaged in dust thermal emission. And in that disk, there's this giant cavity, this gap in the disk. And in that gap are 2 point sources, PDS-70 B and C. Those point sources appear across the spectrum. They're both roughly 3 Jupiter mass planets. And I'm going to try and reproduce their SED. I'm going to focus on the broadband emission in the infrared and the millimeter. There's some H alpha line emissions, probably coming from an accretion shock I'm not going to worry about the line. So here it is. These are SEDs, lambda L lambda. And just to orient you, I've shaded the near-Chem, Mirian, all pass bands. The crosses are the data. So yeah, here's the near-infrared fluxes. There's the millimeter flux. And then overplotted on here, the solid curve. That's a model that we've calculated of an SED of a planet which is accreting from a circumplanetary disk. I'll give you more details on what's going into the models in a few slides. So this millimeter flux in this model is coming from a circumplanetary disk on the planet. It's cooler. And then the near-infrared flux is coming from the planet, the surface of the planet. Not the passively cooling interior of the planet, but from thermalized gas just behind the accretion shock. The m dot going into all of this, the solid black curve, is 0.6 Jupiter masses per million years. You can compare that to your most naive guess for what the accretion rate should be, which is m over t. The planet mass is 3 Jupiter masses, the age of the disk is 5 million years, so 3 divided by 5 is also nicely 0.6. So your simplest guess for the accretion rate actually works to fit the SED. Yeah?
Sorry to explain this. What are the upward pointing triangles?
Oh, yeah. This is the upward pointing triangles. In near-Chem, this is like 11.5 magnitudes of contrast with the host star. We were trying to get some handle on what near-Chem could do. This is roughly 12 magnitudes of contrast with the host star. And that's 110 microjanskis, which is what Sean Andrews says ALMA can do. Does that answer your question?
I think so.
Yeah.
So the lack of data points, for example, in Miri. Well, actually.
I would like to see this system imaged in the mid-infrared.
Okay. So
Yeah.
that hasn't been done yet. But
Yeah. I think yes. It has not been imaged yet in the mid-infrared. Yeah. Okay. So there's another m dot to compute, which is the m dot from our new scaling relations, the max m dot. And when you plug in numbers, this thing, 3 Jupiter masses, it's in that most massive regime that we studied. M dot goes like m to the 2/3. But you plug in numbers, and you get an accretion rate which is of the same order, Jupiter mass per million years. Yeah, Matt.
So you said, so for the computing this, the maximum m dot, you say it's embedded in this, sea of gas, maybe it reaches, the Hilsford reaches out, or whatever. But at the beginning, you were saying that these planets are in gaps in the disk.
Yeah.
So
gaps aren't empty. The gaps have stuff in them. There are deficits of emission, but they're not totally empty. So we have some handle on what how much gas is in the gap from CO imaging. So that's where that row comes from.
okay, so that's even after.
Yeah.
How much is the density smaller than the density fell away?
It's about in surface density, it's I think about 2 orders of magnitude, the cavity versus the just outside. Yeah. There's spatially resolved CO images of the disk. I should say, just to Max's question, the relevant row in all of this is the row in the gap. You're eating off of, and we see it in the simulations. The streamlines that feed the planet are the streamlines of stuff from the co-orbital material, stuff in the gap. So we have 3 m dots, and they all seem to line up. They're all about a Jupiter mass per million years. So we think, we feel kind of encouraged for PDS 70. I think it's maybe evidence that maybe gas accretion really does happen at close to this supply limited m dot.
Where would you expect the accretion shock to be?
Yeah, so in this model, the accretion shock is 4 RJ. It's more or less the surface of the planet. We're interpreting it as basically the surface of the planet where the accretion shock is.
Right, so why can you discount that in the SED? Just scaling from the stellar case, if I had, the same 10 to the minus 6 per unit mass, that'd be a walking accretion shock.
Sorry, I'm not quite sure I follow. In this curve here,
It's 1 micron.
sorry, this SED that we're calculating here, that is where the location of the accretion shock is a free parameter, fit to be about 4 RJ.
The radiation from that is included in this, or I thought you said
Yes.
it wasn't.
So there's a non-thermal component. There's a line, and there's line emission. That line emission is not included. There's a thermal component. That is.
You are including.
Yes. Yeah.
Is that the only constraint we have on the radius of the planet, or is there some independent constraint on the planet radius?
There's theory, but there's cooling and contraction models. But other than that, that's the only thing I can think of as a constraint on R.
Maybe following up on Lynn's question. So is there optical imaging of this planet?
There's the H on it.
There's H alpha.
Yeah.
Yeah.
But I guess.
Nothing in the continuum.
Okay.
Yeah. I mean, you see the flux is falling off. Yeah. Okay, so you can try and do a similar exercise for the rest of these like suspected gap opening planets, the D-sharp planets. So here, every entry in this plot is a suspected gap opening planet. I'm plotting not m dot now, but m over m dot, so it's mass doubling time. And just a couple comments. If you land on the right-hand side of this plot, that's a doubling time which is very long compared to the age of the system. So all of these are normalized. Sorry, it's cut off. T double divided by T age. All of these ages are like a million years for these disks. So that's fine. It just means you're basically done forming. Interestingly, though, most of these points, they plot towards the left-hand side of this figure. These are doubling times which are very short compared to the ages of the system. So we interpret this to be a problem because what are the odds that you're catching all of these things in a super short-lived phase of really rapid growth? So we have one possible solution to this problem, and it's that all of the masses have been overestimated. All of these masses are coming, we've compiled them from other people who have run planet disk simulations to fit the widths of these gaps. All of those simulations, they're always assuming an alpha disk. They assume something about the viscosity of the disk. But you're out there at 50, 100 AU. The parentheses, the numbers in here are labeled orbital radii. It's way too cold for the MRI to operate. It's not clear that there is a turbulent viscosity at all. So maybe it's just a bunch of small planets carving really deep gaps. This is all relevant because Bondi. M dot goes like m squared, so the doubling time goes like 1 over m. If everything else is the same, it's just the masses have been overestimated, then all of these points will shift to the right. And they will be more in alignment with PDF 70, for which the doubling times are of order the system age.
For some system, you only see the fact of
Yeah, so these error bars, they're not quite error bars. They have physical meaning attached to them. So the range accounts for two things. One is mass. So you need the masses to be towards the low end, or maybe overestimated by a factor of 10. And then the other is getting a handle on the gas density in these gaps. Tricky because it's all CO. And CO, to convert to H2, you need a CO to H2 conversion factor. So there's actually physical meaning in these error bars. They mean something about whether CO is depleted in circumstellar disks, about CO chemistry and freeze out. Yeah, we sort of need the masses to be overestimated by factors of 10 to 30. So maybe they're all like Earths running around in these gaps. And CO is close to interstellar proportions. That's what that means. Yeah.
You know, misinterpreting, but couldn't it also just be considered as like they're done accreting?
No, you're on the other side.
Yeah,
this
okay.
side is done accreting. This side is like really fast accretion.
Oh, I see.
Yeah. Okay, I'm going to continue with these sort of run-of-the-mill gap opening planets. People are trying to look now, they're trying to directly image the planet in the gap and get more PDS-70-like imaging. And we want to offer some perspective on like what wavebands to find them in. So like I said, maybe these are smaller things. They're accreting in this Bondi regime where the flow is spherically symmetric around the planet. So here what I'm doing is I'm taking a planet, it's modeled as a black body emitter, and it's radiating at the center of this spherically symmetric Bondi envelope. And then you compute the SED on the outside, process that black body SED through this dusty envelope. And we're doing this with this radiative transfer code, RADMC. So these are more SEDs. Let's look at an optimistic case. So I'll do a 100 Earth mass object, and I'll do this solid curve. So in the near infrared, this curve sits a factor of maybe 5, 10 above this near cam detection limit. This is 4.4 microns on JWST. And might even be able to catch it at the blue end of MIRI, comparing the solid curve to the triangles. I should say that to get this to work, the solid curve, I had to deplete the amount of dust in the envelope a little bit. This is a 10th solar in metallicity. If you go to really dusty envelopes, the dust in the envelope kills off all of your near-infrared power. That's this dash curve here. It attenuates everything. That power doesn't disappear, it just gets reprocessed out to longer wavelengths. The dust heats up and re-radiates it. The problem is it re-radiates it out into the far infrared, 100 micron or so. But it's at those very same wavelengths where the circumstellar disk, heated by the star and not the planet, 50 Kelvin or so, is brightest. So this red curve is the SED, not even of the entire circumstellar disk, just a little patch of it, of scale length H, heated by the star, and it's way brighter than everything at long wavelengths. So you're competing, at long wavelengths, you're competing against this like really bright background. So better to go to the near infrared, where you have some chance of standing out against the background. Near infrared, blue end of MIRI.
What distance are these?
These are distance from Earth or distance from the star?
Distance from Earth for your flux limits.
That's this is the flux limits are for chronographic imaging contrast limit at 1 arc second from the star. So you can
Okay.
yeah the contrast limit, yeah. So those were envelope models. We've also done DISTI models, maybe more appropriate in the Hill limited regime. I previewed these for PDS-70. These are analytic CPDs that we've constructed. They are heated on their inside by viscous dissipation, and they're heated on their surface layers by radiation from the planet. So it's a bit more complicated now. There are all these temperatures running around for different layers of the disk. But the upshot is the same. The solid curve here is the SED, the final SED, and the upshot is that the near infrared is the way to go. Near infrared, blue end of MIRI. Don't want to deal with the background of the circumstellar disk. So that's going to wrap up the first half of the talk. We have these 3M dots. We think they're maximum accretion rates. They might even work. They might even real things might accrete at near the maximum. And we have these SCDs, near cam and blue end of Miri. Yeah, Jerry.
How about the background from scattered light?
Yeah, I'm glad you asked. It depends on the grain sizes. If it's 0.1 micron, it's very sensitive to grain size. At 0.1 micron, for 0.1 micron grains, we're finding it's not important. Okay. At a micron, it starts to become competitive. The planet and the scattered light background start to become competitive. Okay, I'm gonna just keep going. Talk about these interplanetary systems inside of an AU. So Kepler and now TESS are discovering these sub-Neptunes in abundance. These are 10-ish Earth mass objects. And a cool feature of them is that they come in families. So 3, 4, 5 planets all orbiting inside of an AU. And that's not even counting their more distant companions, these cold Jupiters, whose occurrence rate seems to shoot up if you control for the presence of an inner sub-Neptune. So you should think of these planetary systems inside of a few AU as crowded, dynamically active systems. Here's how these neighboring planets space apart, neighboring planets in the same system. This is measured here by their period ratio, P2 over P1, for neighboring bodies. You can see for the most part, there's this whole continuum of values that you get. I've highlighted a few of the first order mean motion resonances, but for the most part, the distribution doesn't care about the resonances. That being said, there is this excess in the distribution near the 3 to 2. And famously, this excess is not right at 3 to 2. It's at 1.5 to 1. It's asymmetric. This excess is just wide of the resonance. So these are planets which are just a little bit farther apart than a perfect integer ratio in their periods. This preference for being wide is even clearer when you look at the 2 to 1, for which there is a stark trough in the distribution, just narrow of the resonance. There might be a similar trough for the 4 to 3. Okay, so the insight here is just stacking data for the 3 to 2 and the 2 to 1. Delta is our measure of a fractional deviation from a perfect integer ratio in your orbital periods. And characteristically, these resonance systems pile up at positive 1% in delta. So this is what things look like today. These are mostly few billion-year-old stars. Here's a plot that Fei Dai shared with us, studying multi-planet systems around younger stars. These are 0.1 billion years to 1 billion years old. And Fei is finding that the fraction of resonances shoots up. 40% now of planets are in these resonant peaks, compared to 10% today. So they still show this offset, this asymmetry. They like to be a little bit wide of perfect integer ratios. You go to even earlier times now, less than 100 million years. And small number statistics, there are 6 systems, but 5 of them are in resonance. So it's a monotonic trend. Resonances become more common as you go back in time. Or put another way, the resonances seem to be breaking. Again, though, this preference for being wide, that's universal. So we want to explain both the drop-off in the resonances and the asymmetries about the resonance. So the asymmetry is easier, so I'm going to do that first. When these asymmetries were first reported, they were reported as this mysterious thing, but it's actually perfectly natural. Resonances prefer to be wide. And I have a series of movies here to illustrate this. This was first recognized by Goldreich in early studies of the resonances of the Galilean moons. So in all of these movies, I have an outer planet in blue and an inner test particle in pink. And at time 0, I'm going to initialize things so that the test particle is at pericenter of its orbit. So I'm going to mark peri with this black dash here. And at time 0, I've also initialized things so that the planet and the test particle are at conjunction when they lie along the line at their point of closest approach. The name of the game in all of the movies is to get the conjunctions all of the future conjunctions, to keep being at parity. Because everything is symmetric about parity. If you keep meeting back up there, then all of the angular momentum exchanges just before and just after parity will exactly cancel out, and the whole system will be strictly repeatable and stable and periodic. So this first movie, the period ratio is exactly 3 to 2. I'll lay down a green X every time there's a close encounter, and there it goes. Okay. You'll keep meeting back up at parity because you started there. No choice. What this first movie is missing is precession. Parity is actually moving. The next movie, period ratio is still 3 to 2, but I've folded in precession onto the inner planet's orbit. And you see, you will keep missing parity. And there it goes. The conjunctions will sort of pepper throughout an orbital phase. Your timing is all off because parity is moving out from under you. So the way to regain your stability is to adjust your spacing a little bit, to adjust your timing. So the last movie, period ratio is a little larger than 3 to 2, and you will see that the conjunctions will happen, boom, always at the same point in orbital phase, not the same point in inertial space. They'll happen wherever parity is. So the equilibrium of the resonance, whenever we're talking about these first order resonances, the equilibrium is always wide of a perfect integer ratio, at least at low eccentricity. And just to put a pin in it, in particular, it's the fact that parity is moving backwards against the orbit. It's an epsidal regression. That's what sets the sign. That's why the equilibrium is at positive delta.
As you have an equation there, the delta should be omega over the orbital frequency.
Yeah, that's.
And if the precession is due to the existence of the other planet,
Yeah.
then you expect that to be around m over m, the mass of the planet over the mass of the star. So around 10 to the minus 3. But the observations tell you about 10 to the minus 2.
The precession rate is of order, it's not of order mu, it's of order mu over e.
Mu over?
Over e. At the fixed point. At the resonant fixed point, cosine phi is 1. So the precession is mu over e times the mean motion. Yeah.
Why are you expecting the precession to be retrograde?
You can understand it geometrically. Just look at this encounter. Okay. These are all planet-planet induced precessions. You can look at this encounter. The planet tugs on the test particle outwards. So you pick up a positive radial velocity. If you have a positive radial velocity, you have to be moving away from parity. So there's no choice. The epsidal line has to have regressed. Other questions?
Yeah. So here, your system seems to be like a circulating regime, but will your results change if there's like a librating?
This is circulation.
Right.
This is ligration. Okay. This is the fixed point. This is ligration with 0 resonant ligration amplitude.
So yeah. the cutoff, then whether it would be in an excess, like whether the delta would be positive or negative, is therefore to keep it within the librating regime, right, and not let it cross over into the circulating regime, which is why it's opposite on the two sides.
You can have things as I'll show you actually. You can have things which are at positive delta, but which are formally the resonant argument is in circulation. But how should I say it? First, the way this usually works is first you drive it to the fixed point, you kill away its ligration amplitude, then you're stuck at positive delta, and then you can make the resonant argument do whatever you want by kicking it around. Other questions? People here like dynamics. Okay, so big picture, here's what we're thinking. Big picture, this high resonant fraction at early times is to us a smoking gun of the protoplanetary disk. All of this stuff that I did, this is just the equilibrium of the resonance, the fixed point. But I mean, the resonance is literally a pendulum. I'm going to keep using a pendulum analogy. And pendulums, like, they'll swing forever, right? Unless you give them some friction to damp down to the equilibrium. So the friction, we think, is coming from the protoplanetary disk, which exerts a gas dynamical friction force on the planets. Okay, that dynamical friction takes the form of orbital migration and eccentricity damping on the planetary orbits. So it establishes an equilibrium at positive delta, which depends on the ratios of these two time scales. In any case, the disk traps things into resonances. But the disk isn't there forever. So at some point, the disk goes away, and what happens then? Here's a series of planets locked into mean motion resonance with each other. This is an n-body simulation that I ran. And then you wait 10 million years, and the system has gone dynamically unstable. And again, at 50 million years. So without eccentricity damping from the disk to, like, eccentricity damping is protective. It stops things from going haywire. It keeps you on nice circular orbits. So without that eccentricity damping, all hell breaks loose. So this is big picture what we're thinking. Resonance capture, and then over the long term, over hundreds of millions of years, resonances are starting to break. I'm going to try and, like, flesh out this picture a little bit now. Try and, like, understand what it takes to break the resonances apart, and then also show you that in some cases, you don't totally break the resonance. You just sort of pull at it, and then you leave, the resonance survives, and you sort of, like, shaking. And you can see that shaking, that ringing, in the transit timing variation data. Okay, so instabilities. If you want to stabilize against the instability, the way to do it is to get rid of planets. Once the instability sets in, you whittle down the number of planets. And there's two ways to get rid of planets. One is to eject things, the other is to merge things. But all of this is happening close to the star inside of an AU, and so the preference is to merge objects together. The potential of the star is just too deep, close in. You can check this by comparing the escape velocity from the system to the escape velocity from the surface of the planet. So mergers, and not ejections. We thought, well, these 100 million year integrations, it takes forever for the instability to set in. It's long-term chaos. But we kind of know how things end. They end with mergers. So we thought, like, let's just skip to the end. You're watching a show and then you start it, but not, like, good enough to watch all 8 seasons. But you really want to know how it ends. So you watch the last episode of the last season. That's what we're trying to do here. Okay. So the way this works, we take a pair of planets. They are locked into resonance. Here they are. Here's their period ratios, just wide of 1.5. And we're doing this for, like, hundreds of systems with n-body. And then we say, let's watch the final episode of Game of Thrones. And you send in a third body on just some wildly eccentric orbit. That eccentric orbit triggered by some dynamical instability that took hundreds of millions of years to set in. So we're not simulating everything that happened before that point. This trajectory goes unstable very quickly. These integrations last hundreds of days, not hundreds of millions of years. Here I'm plotting what happens after the collision. After the collision, if the interloper is comparable in mass to the mass in the resonance, you just obliterate the resonance. So you get this whole, it's nice for forming this whole continuum of period ratio values. And if the collider is less massive, then you sort of smear out the peak. Our goal, by the way, I should say, our goal is going to be to go from this distribution, which is what the data tell us, everything locked into resonance at early times, to what's observed today. That's where I'm going. There are other kinds of collisions you can consider. Maybe the third body doesn't come in on this, like, crossing crazy orbit. Maybe its eccentricity gradually increases with time and then starts to graze the orbits of the resonance. This still leads to a collision pretty quickly, but now because you're coming in from the outside, after the collision, your period ratios face apart a little bit, just wedge apart. So what we're trying to do here, this is all in progress work. What we're trying to do is like understand how often collisions have to happen, what do the colliders, the mass ratios in the collisions have to be, what kinds of trajectories do you have to get to go from here to here. Before I show you an attempt to fit the data, let me talk about even more data, another piece of the puzzle. These are the transit timing variations. So this is real data from Kepler. Every point here is a transit of this star, of this planet, Kepler 58b. It transits its star on average every 10.2 days. I say on average because the transits aren't perfectly periodic. There's this neighboring planet, 58c, which is in resonance with B. So the y-axis is plotting how early or how late the transit happened compared to the strictly periodic orbit. So when B arrives a little bit early compared to the mean orbital period, C arrives a little late, and vice versa. So they're like a pair. So these fluctuations for the two planets are anti-correlated. These are sine waves, so they have amplitudes and periods attached to them. Both the amplitude and the period scale as 1 over this delta parameter. This is why we only detect TTVs for objects which are very close to resonance. So these planets, they are in that peak, that resonant peak of the data, the 3 to 2 resonant peak. TTVs are amplified to the point of detectability only near resonance, or usually near resonance. So lots of people have done the amplitude and the period. I'm not going to talk about them more. They fit them. Instead, I want to talk about the third property of sine waves that everyone forgets about because who cares about phases? Phases are just some constant offset. Except for TTVs, they actually carry information. So to define a phase, you need some special point in this cycle. I should say, the phase I'm talking about is not the relative phase between these two. That's always 180 degrees. There's a single phase in the same way that there is a there's a single period to the oscillation. So to define the phase, you need some special point in the cycle, and nature offers that. That point is when both planets transit the star at the same time. B and C transit together. You can actually make out this double transit in the data if you are willing to squint a little bit. Let's look at this first transit of B. B is transiting. I've dropped a vertical line down, and if you squint, you will see there is no corresponding transit of red. So you do it again. Now red is transiting, but it's sandwiched in between two transits of blue. And again, keep missing each other. It's like this game of phone tag. You call someone, but they don't pick up because they're in a meeting. So they call you back, but then you're in a meeting, and you keep doing that over and over and over. But every once in a while, you're both out of meetings, and look, you're both transiting. Double transit. And as promised, they happen exactly once per cycle. So here's another one. Red and blue transiting together. So the phase of the TTV, and now this is just a definition part, I'm going to use the zero crossing as a reference point. And the phase is going to be the phase difference between these two lines. This is what I would call negative 60 degrees of phase. 60 degrees of phase between these two lines. Here are more examples of phases. This is the one I showed you, negative 60 degrees. Here's positive 60 degrees, so the double transit happens just after the zero crossing. And here's an example where the phase is 0. Double transit happens just as the sine wave is crossing 0. Here's the distribution of phases measured from Kepler data. You see it is clustered around 0. But there's also serious spread. 60-degree phase shifts are pretty common. These phases, the phase shifts that we're measuring, they are telling you that something has like shaken up the resonance. I think that something is collisions and neighboring bodies. You take a pair of planets, you drive them with some orbital migration, some eccentricity damping, and you capture them into resonance, you will get zero phase shift in the TTV. It's a reflection of the symmetry of this peri-apo configuration at conjunctions. These phase shifts, which are observed in the TTVs, they tell you the conjunctions are not happening where you thought they were happening. Something, to use a pendulum analogy, the pendulum is swinging. That's what the phase shift tells you. For those who know what I'm saying that the resonant migration amplitude is non-zero. You can tell from the phases. The free eccentricity is non-zero.
Wait, but I thought the observed systems are not actually in resonance line.
It depends on what you mean by not actually in resonance.
Delta is bigger than the resonance.
There is still a resonant argument that can be defined, and they're in that peak of the period ratio distribution. The phases tell you that the resonant argument is in libration or is librating with order unity amplitude. Which I think is somewhat surprising, because to get into that peak of the data, into the period ratio peak, you needed some dissipation to drive you there. So here's now an attempt to fit both the period ratios and the phases together. So here what I'm doing, again, I'm starting everything locked into resonance. So everything starts at a period ratio just wide of 1.5 and with zero phase shift. But then I send in colliders. So here what I'm doing is I'm assuming 90% of the collisions are with they're major mergers, comparable mass object. They destroy resonances. They form this continuum of period ratios. But then in 10% of systems, I'm assuming that the collider is kind of minor, 10th of an Earth mass. These 10th of an Earth mass objects, they're not enough to kick things completely out of this peak. So you have this remnant peak now in the period ratio data. But they're enough to like nudge the resonance, get the pendulum swinging again. And you see it in the phases. It's like ringing. I think of like the ring down or the ringing of a black hole after a merger. Okay, I have a couple final minutes. So I'm going to do some more dynamics, which apparently people here like. Just before the collision. I've been skipping to the end, right? Just at the collision. Just before the collision, this third body is on an eccentric orbit. And turns out you don't even have to wait for the collision to produce one of these phase shifts in the TTV. The gravitational forcing, the secular gravitational forcing from this third body will be enough to perturb the resonance in some cases and phase shift the TTV. And I'll just highlight some of the dynamics of the system and show how it might be relevant to some observations that we're finding. So the way this works is I take a pair of planets, 10 Earth mass planets, I apply some gas dynamical friction, some migration, some eccentricity damping. Here they are capturing 1% wide of the 2-to-1 resonance, and here's their phase shift damping to 0. But then this dashed vertical line marks when I take away the friction, because the disk isn't there forever. Now I've got this third body on an eccentric orbit. The secular eccentricity forcing from this third body causes the phase shift now in the TTV to cycle. There's a whole range of phases that you can get just for one system, because it depends not only on time, but notice the phases here, they are oscillating about the apsidal line of the third body. So it also depends on viewing angle. So this is the whole range of phases you get for this one system. So you're perturbed even before a collision happens. The other thing I want to highlight is the alignment of the resonance. Okay, so you see it in this cartoon too. The Kepler ellipses here of these two resonant planets, these two sub-Neptunes, they're aligned and they're rigidly precessing together. For those who are familiar, this is just the opposite of the usual resonant equilibrium, which is always peri of one and appa of the other. It's always anti-aligned. So there's this aligned secular precession. Most of the time, you can't measure epicidal orientations from transit data. But we were pleased to find that in the two systems where people have been able to do it, so you take a resonant pair of planets. These are objects in the resonant peak, the 3:2 resonant peak in the period ratio data. In both of the systems where people have been able to pin it down by combining transit data with other things like radial velocities, they have found aligned apses. Just the opposite to the usual fixed point. Aligned apses in K219, and in this is Kepler 90. Resonant pairs of planets with aligned apses. Okay, last slide. Just want to point out that there's, like, we didn't just make up the third body. There's a lot of third bodies out there. These are their masses and their orbital periods. These are neighboring planets which are neighboring resonant, known TTV resonant systems. And we've scoped out, using these sorts of calculations, what their masses and orbital periods have to be if they're going to produce these phase shifts in the TTV. And gray on the spot is bad, and white is good. And you see most of the points here in the white. Now everything depends on how eccentric they are. So we're asking for eccentricities of 5 to 10%, if they're going to be responsible for these phases. So I'm going to end there. Here's the timeline we're thinking of. Resonance capture. Just before the collision, there's some secular eccentricity forcing. So all of these guys might be on their way to colliding in the next 100 million years. And then you end with the collision, you end with a bang. And yeah, that's all. Thanks.
Yeah, a lot of questions at the top, but we can go a couple more minutes. There's no questions anyone has? Yeah.
What's the prescription you're using for dynamic?
A dot and E dot imposed on some time scale. In n-body calculations, you impose it as an extra force at every time step. Yeah.
So do you manually set the time scale?
Yeah. We're not doing type 1. All the resonance really cares about is A dot and E dot. So yeah.
The two systems that you said were found to be aligned in axis. Do they have a third body that's known?
Yes, both have third bodies. Kepler 90 has a whole bunch of third bodies lying around. K219 has at least one, which I admit is probably, unless it's very eccentric, is probably too small. But there are that's one known. I don't know what's on the outside.
The small colliders exciting the resonances, I buy it for 2 planets, but when you add more and more planets in the resonant chain, it seems like it's harder to kind of gently shift it without breaking everything. Have you looked at that at all?
We haven't quite done chains yet. What I will say is that the TTV systems, all of the phases that we're looking at, for those are really like 2-planet resonant systems. You don't get simple sine waves for TTVs unless you have 2 planets in the resonance anyways. We haven't done this for chains yet. That answers your question.
The phases as you define them, they depend on the azimuth of the observer.
Are they independent of the azimuth? No. An observer from a different line of sight will measure a different phase. If the resonant libration amplitude is non-zero, If the pendulum is swinging, there are every observer will measure a different phase. But the more the pendulum is swinging, the broader the distribution of phases you will measure will be. Does that make sense? If the resonant vibration amplitude is 0, there's 0 free eccentricity in the resonance, everyone will measure 0 phase. And the more the pendulum is swinging, the more.
Even though the double encounter will happen at a different time for different observers.
Yeah, that's why you measure different. That's why different observers will measure a different phase.
Even if the phase as you define it is 0, an observer from a different azimuth will also measure a different time of double encounter.
The phase is 0. Sorry, I have to think about it a little bit. I'm about as certain as I can be that once I think about it, I will be able to explain why. As long as the double encounters are happening at peri and at apo, you will always measure 0 phase once you have mapped out a full TTV cycle. Because it's symmetric. So conjunctions are at peri and apo, you're going to get a symmetric TTV, which is 0 phase. Let me think about it a little more. Yeah. Seems solvable.
All right. So yeah, Nick will be around for the whole day. So if you want to talk to him, feel free to do so. Yeah, let's thank Nick again.